Hi, my name is Arisa,
And I'm Megan.
and we're juniors here at Iolani School. For our K Fellowship project, we decided to create a bioplastic alternative for six-pack rings from food waste.
Thank you to Papa Jack for giving us the opportunity to do research on something we care about this summer. We both enjoyed K Fellowship and are so grateful for this experience. Due to increasing population and continuously improving living standards, plastic production has increased from 0.5 to 260 million tons per year since 1950. 4 to 12 million metric tons are added to the percentage of plastic in the ocean each year, accounting for 80% of all ocean pollutants. Plastic is often mistaken as food and is often found around the necks or bodies of almost any sea creature. If plastic is consumed by a marine animal, it can reduce food uptake or cause internal injury as a result of blockage of the intestinal tract. We spend much of our time utilizing the ocean for our own personal pleasure, such as swimming, surfing, and snorkeling, but never take the time to make sure future generations are able to enjoy these same recreations. We need to make sure the ocean that does so much for us is able to give just as much to future residents as well as its inhabitants.
Plastic rings, commonly found on six-packs of aluminum cans, were invented 40 years ago and popularized for its ability to speed up the production and packaging of the beverage cans, which they hold together. Despite this, these rings have a major impact on marine wildlife. In 1987, 1 million seabirds and 100,000 marine animals were discovered to have been killed each year from plastic six-pack rings alone. A year later, 1,500 six-pack rings were found on a single beach over the course of 1 hour.
Current plastic rings are typically made from LDPE, which is a lower density form of polyethylene. Polyethylene is a commonly used plastic material because it is light and versatile and consists of a simple structure that is repeated many times, which gives it its plastic-like properties. Despite great uses of plastic, the production and incineration of polyethylene has major negative impacts on our environment. LDPE is often used as an alternative to polyethylene because it is photodegradable, meaning it will degrade, but not completely, and only under conditions in which they are exposed to UV sun rays. This makes LDPE less than ideal for use as a plastic ring because of the uncertainty of its biodegradability, despite it being a step up from traditional polyethylene.
Bioplastics consist of at least 20% recyclable materials, which reduces the use of fossil fuels, leaving a smaller carbon footprint and resulting in a faster decomposition process. It is less toxic because it does not contain the hormone disruptor, bisphenol A, which is found in common plastics. The two most common types of bioplastics are PLA, which is made from fermentation of a carbohydrate source such as cornstarch, and PHA, which is made by manipulating microorganisms. Current bioplastics present a solution to many of the problems created by traditional plastic, but still create many problems of their own. Because many bioplastics are created from crops, a great amount of pesticides and fertilizers are used. Also, the biodegradability of many of these plastics rely on high temperature industrial composting facilities, which many of these plastics will never reach. Lastly, bioplastics are costly. They can cost up to 50% more than traditional plastic because of their intricate production process.
One example of a six-pack ring already made from bioplastic is the E6PR or Eco Six-Pack Ring, which was created in 2017 and is constructed of barley and wheat waste from the brewing process, along with natural fibers which are biodegradable and compostable. Because they are made from compostable materials, they are not harmful if ingested by animals and degrade within a matter of days if disposed in a composition facility and within a few weeks if left out in the environment. However, E6PR is expensive to produce.
Another problem plaguing our Earth is food waste. The amount of food waste in the US has drastically increased from 1974 by about 50%. Worldwide, 1/3 of all food produced is wasted or not consumed, as estimated by the United Nations Environment Program. Large amounts of food waste lead to unnecessary consumption of fresh water, land usage, and chemicals, such as pesticides and fertilizer. Food is the most common form of waste disposed of in landfills, where it produces methane, a greenhouse gas that contributes to global warming. If we limit the amount of food we waste, we can save money, save energy, and help to reduce greenhouse gas emissions.
What can be devised as a cheap, eco-friendly alternative for the plastic rings on soda cans that will repurpose food waste and reduce the amount of harmful plastic which enters our oceans? We plan to address these two major global issues by designing an alternative for the plastic rings found on soda cans made from food waste. Despite the many trials and studies that we have already encountered on this topic, we have found that existing alternatives are either expensive to reduce or have a detrimental impact on our environment, similar to traditional plastic. We can minimize the amount of non-biodegradable plastic that enters our oceans while also repurposing food waste by creating a cheap, eco-friendly alternative for the plastic rings on soda cans.
We tested several types of bioplastic based on starch and cellulose monomers, derived from banana peels, potato peels, and orange peels. We used the procedure cited in an article we found to create a sustainably sourced, biodegradable, and cheap bioplastic.
We first tested the banana peel bioplastic procedure using pre-purchased ingredients to fine-tune our experimental process. For our first banana trial, four bananas were peeled and weighed. We then boiled the banana peels on a hot plate and dried them with paper towels and an incubator. The peels were then pureed in a blender and mashed with a mortar and pestle into as uniform of a paste as we could achieve. The paste was mixed with hydrochloric acid, glycerol, and sodium hydroxide. Lastly, the paste was flattened into a petri dish with a spatula and placed in the oven until it was completely dry.
The results of this method were mildly flexible, but not very strong. When pulled on lightly, the outsides didn't break, but the middle was undercooked, so it broke very easily. The plastic also had very noticeable fiber strings from the peels and a dark and unpleasant color, which made the plastic look quite unappealing. Overall, the plastic was not terrible, as it also had no smell and good flexibility for our first attempt. Next, we tested two methods for potato peels. These two methods generally required the blending and centrifuging of potato peels, along with the addition of vinegar and glycerin.
The first potato method had decent flexibility and strength. Out of all of our methods, it felt the most like a traditional plastic. However, the yield was small considering the amount of potato peels we used. The final product was about the size of the palm of a hand and fairly thin. The results of the second method did not completely dry, so we decided that this method would not work for us. Because these methods require a lot of work, including centrifuging, drying, and heating the peels, and has a high production cost because of the centrifuge, it would not be realistic to consider this a cheap and easily made alternative for plastic rings.
We followed up on our potato peel trials with the orange peel method. This method involves sun-drying orange peels, agitating them with HCl, and heating them on the hot plate. This method was not successful for us as large amounts of acid were needed for a small amount of orange peels, which produce little to no pectin. Early on, we realized this method would not work in the long term because of its high demands for work and materials with low yield.
After testing all three bioplastics, we chose to develop the banana method because it had the simplest procedure, the best strength, and greatest yield per original material. We made various changes to improve our method in different ways. One change we made was adding water before blending the peels, which allowed the mixture to blend more easily and create a smoother paste. Another change was adding cornstarch to two groups of our recipe, one with fibers from the peels and one with fibers removed with a strainer, which gave the plastic a more presentable look. We found that the group with both fibers and cornstarch was the strongest and decided to continue with that one as strength was a more important factor to us than visual appeal.
After many trials and modifications, our final banana method started with peeling 3 bananas and weighing them. Then the 3 banana peels are boiled on a hot plate and then blended. Next, the mixture is boiled again to drive off the water and make the plastic thick. After boiling, excess water is pressed out of the paste with paper towels, and HCl, glycerin, NaOH, and cornstarch are added. It is then left to dry on a baking sheet for 2 to 3 days.
Next, we started work on our molds and began by enlisting help from Mrs. Hattori, a teacher in our school's fab lab. We then took the measurements of the rim around an aluminum can, as well as a plastic ring we already had on hand. Mrs. Hattori was a major help in creating our mold, as neither of us had any experience in 3D printing. After printing our mold, we realized making the middle section of each ring removable would make it easier to remove our bioplastic after it dried. We used our final batch of banana bioplastic to fill the mold. The following day, however, we noticed that the bioplastic was already shrinking and at a rapid rate. We poured on another layer of banana bioplastic, but unfortunately, when we returned after the weekend to check on it, the paste was completely dry and broken into several pieces. Although we made adjustments to our mold to account for this, it continued to shrink when we left it to dry.
We tested our bioplastic for water absorption, biodegradability, and strength against 3 different controls: E6PR, bioplastic forks purchased from Amazon, and traditional plastic rings. The water absorption tests were conducted by approximating a 1/2 inch by 1/2 inch square of plastic and placing it in a beaker with 4 milliliters of ultra-pure water. Each sample was masked prior to being put in the water and recorded. 1 sample of each plastic was taken out each day for 3 days and masked. On the graph, the blue represents banana bioplastic trial number 8. As you can see, the water absorption of our bioplastic seems less than ideal considering that the mass of the plastic almost doubled. However, after the water was absorbed, the plastic was much less tough and thick, showing the plastic's ability to degrade if it was left in an ocean environment.
Next, we tested the biodegradability of our final 2 banana bioplastics. After weighing and recording the mass of each 1/2 by 1/2 inch square of plastic, we used a small patch of soil in our school's garden to bury 9 samples of each plastic. 3 samples of each plastic were taken out on each day for 3 days. The plastic was then allowed to dry for a few days to allow the absorbed water to evaporate and get an accurate reading of how much had degraded. Our banana bioplastic showed a huge improvement from the biodegrading capabilities of our controls, which was a mere percentage of ours.
Next, we conducted strength tests using a materials testing machine, which we use for tensile testing. Samples from banana trial number 8 and 9 were cut into short strips to fit into the machine and then measured for width, height, and length. The pink in the graph shows the results of trial number 9, which could take more force before it broke, but did not stretch as much as trial number 8. While the amount our controls were able to stretch was roughly the same as our bioplastic, the stress the bioplastic forks could take was 36 times, the E6PR 30 times, and the plastic rings 12 times as much as trial number 9 of our bioplastic. In conclusion, our bioplastic could stretch just as much as our controls before it deformed, but needs much improvement in how much force it can take.
The main purpose of this experiment was to create a bioplastic for soda can rings, which requires little equipment and skill, has a low production cost, is biodegradable, and strong enough to hold the weight of the cans. All of the supplies, including an electronic balance, beakers, and hot plate, can easily be obtained in many schools or facilities, and no special skills are required to make our bioplastic. The plastic does not take very long to make either. It took us about 2 hours to make 1 batch, but the size of the batches could easily be doubled or tripled and require the same amount of time. All of the equipment and materials, including cornstarch, bananas, and a blender, were well within our budget and would be easy for many to obtain. Also, the biodegradability of our plastic far outshined that of any of the controls we tested it against.
2 major lessons we learned from this project were to always have a plan B and that trial and error is important. Throughout our experiments, we constantly ran into problems we did not see coming. For example, the limited strength of our plastic and the amount it shrunk while drying. Despite these hurdles, we stayed focused and resilient because we always came up with another plan. In the end, our experiment consisted of about 11 trials, which were often repetitive with minor changes, so the work at times were menial. However, we reminded ourselves this was all part of the process and continued to work for the goals that we had set.
In this project, there were many possible limitations. For our project, we used many banana peels, all of which were at various stages of ripeness. This could have affected the overall result of the bioplastic because starch content of banana peels vary as they become more ripe. The amount of time we left the bioplastic to air dry or incubate could also have had an effect on our results. Because we couldn't always be at school, we were unable to check on our bioplastics constantly. This led to different durations of incubation and air drying, which could have influenced the outcomes of our trial.
Because we did not fully accomplish our goal of making a biodegradable six-pack soda can ring out of banana peels, more research will be required in the future. We will need to further investigate why our banana plastic shrinks such a significant amount and how this can be remedied to keep it from breaking. Additionally, the plastic recipe we created wasn't nearly strong enough for use as a plastic ring for soda cans, but more research could be done to determine how it could be used as an alternative for other products. We'd also like to acknowledge all the people who helped us conduct our experiments and made this project possible. Dr. Yvonne Chan guided us through our project and gave us helpful advice. Mr. Eric Tong supervised us in the lab and provided guidance with supplies and equipment. We'd also like to thank Ms. Geraldine Hattori for helping us create our mold. Lastly, Ms. Jessica Sailors mentored us every step of the way in our project. Thank you for being a major help in our endeavors and always making the lab a fun place to work in. Thank you.
Thank you.